In this video, we are asked to determine the radius and the interval of convergence of this power series, this given power series. So let's start with the radius of convergence. Remember that the go-to way to try to find the radius of convergence is to apply the ratio test to the sequence of coefficients, the c sub n's, and then interpret that in terms of the center and everything else here. So let's apply the ratio test to these c sub n. So we have c sub n plus 1 over c sub n, absolute value. We want to first write out the ratio itself and then try to maybe simplify it and take the limit. So c sub n plus 1, well, that's just the term that we get when we replace n by n plus 1 here. So that'll be n plus 1 factorial in the numerator. And in the denominator, it's going to be 1 times 3 times 5 up to 2n minus 1 times the next term is going to add 1 to n, but that means it's going to add 2 as a constant. So it's going to be 2n plus 1. Okay, so that's the term cn plus 1. And then we want to divide this by the term cn, but rather than divide, I like to usually multiply by the reciprocal. It seems to be easier and help us with our cancellations a little bit more. So this is then 1 times 3 times 5 all the way up to 2n minus 1 in the numerator. And the denominator is just n factorial. Okay? Now, our goal is to take the limit of this ratio as n approaches infinity. And so right away we can see that we can cancel some stuff here. This product 1 times 3 times 5 up to 2n minus 1 shows up in numerator and denominator both. And of course in a limit we're allowed to cancel stuff. So that's gone. The other thing that we can do is we can notice that n plus 1 factorial, if we were to take out the n plus first term, then what we're left with is n plus 1 times n factorial. Okay, and of course then this n factorial can cancel that one, and we're just left with n plus 1 in the numerator here. So after some careful cancellation, also the other thing we notice is that everything is positive, so we don't need to carry these absolute values with us anymore. But this becomes the ratio n plus 1 over 2n plus 1. And again, our goal is to consider what's the limit of this ratio as n approaches infinity. Well, this is a rational function. It's a ratio, of course, right? But it's a rational function where we just have powers on the top and bottom. We've canceled out everything else. And as n approaches infinity, the limit here is going to equal the ratio of the leading coefficients. So 1/2 in this case. Now, remember that this 1/2 is not the radius of convergence of the power series. This is the limit of the ratio test applied to the coefficient sequence, c sub n. And we have shown in a previous lecture that the radius of convergence of the power series is always the reciprocal of this number. It's 1 over L. So, for us then, our radius of convergence of this power series is just going to be 2, the reciprocal of the limit. All right? So that's the radius of convergence. The next question that we want to know, or that we want to try to answer, is what about the interval of convergence? So remember that the interval of convergence is always, it's an interval first of all, and it's related very closely to r. So it's always equal to x minus x naught less than r in this absolute value sense. It's always at least equal to this, I should say, where the center comes straight from the power series, and for us there's no number there, right? So for us x naught is equal to 0 for this example. Okay, so what we can say then is that our interval of convergence is at least this, so absolute value of x less than 2, and in interval notation that would be -2 less than x less than 2. Well, why do I say at least? The answer is because this could potentially, it's possible that we should include one or both of the endpoints of this interval. But remember that those two endpoints correspond to the points where the ratio test gives us a 1. Okay, the ratio test gives us a 1 in the limit, and it's those times specifically and only where the ratio test is inconclusive. And inconclusive in math always means do more work, right? And so the more work now is that we have to check the endpoints. We know that our power series is convergent on this interval for sure. The question is, what about the endpoints? So let's start with the right endpoint when x equals 2, and what we need to do is plug that into this function, to our power series function, and see if it converges or not. Okay, so we go to the endpoints. So we need to check. Let's start first with f of 2. All right, and as a power series, as a series, f of 2 is going to be equal to n factorial 2 to the n. I corrected myself because this is not going to be a power series anymore. So it's everything we've been working with, all divided by this product. And notice our job, when we plug in 2 for x, it goes into x on both sides, right? And so, like I said, this is no longer a power series. This is a legitimate series that we can test with all the different rules that we've learned so far, right? All the different tests that we've learned. So we are not restricted to treating this like a power series anymore. We just want to know, does this side of the interval converge, right? So let's look at this a little bit more closely. I've put a box around the sequence term here, the general term of the sequence. I want to write this out and kind of examine it a little bit more closely. So a sub n is equal to exactly this, n factorial times 2 to the n over 1 times 3 times 5 all the way up to 2n minus 1. But if we start to expand this out, let's see what happens. So n factorial is of course 1 times 2 times 3 all the way up to times n. And in the denominator we have 1 times 3 times 5 up to 2n minus 1. But on top we also have this term 2 to the n, right? And so what we can do is we can take, so 2 to the n, by the way, means 2 times 2 times 2 n times, right? So this is 2 times 2, so 2 times 2 times 2 times all the way up to 2 n times. What we can do is, at least in our minds, or even legitimately, we can take these numbers, these 2's, and kind of distribute them through this product, and we can see that as we multiply through, each one of these 2's can be multiplied through by one of the terms of the n factorial, and then we can rewrite this and keep everything lined up. By the way, the n factorial and the 2n minus 1, this product on the bottom, have the same number of terms, right? And so as we write this out, this now becomes we multiply by 2. So this becomes 2 times 4 times 6 all the way up to 2n. And downstairs we have what? 1 times 3 times 5 all the way up to 2n minus 1. Okay, and so as we move across this list, we see I've written this so that these are kind of grouped. We have 2 over 1, the top is bigger. 4 over 3, the top is bigger. 6 over 5, again, numerator, or the top is bigger. All the way up through here, where 2n over 2n minus 1, the top is bigger. All right, and so what we can say for sure then is that this limit, since the numerator is always bigger than the denominator, we at least hope that this should be greater than 0, but let's prove it, okay? So we're saying, all right, I think at least this is going to be greater than 0. I'm going to put it in parentheses here, but that's what I want to check. So how can I prove this? Well, one way is to kind of cut this and group it, right? So the next term ahead of this one is going to be 2n minus 2, and the previous term in front of this one is going to be 2n minus 3. Again, the top is bigger, right? And so if I regroup this, I can write this as 2 times 4 times 6 up to 2n minus 2 over 1 times 3 times 5 up to 2n minus 3, all times 2n over 2n minus 1. And what I'm going to do now is apply a kind of squeeze theorem argument and say, well, look at this. This first term, this beginning stuff, is absolutely bigger than 1. Every one of the terms on the top is bigger than the terms on the bottom. There are the same number of them. They correspond in quantity, right? And then in magnitude, the ones on top are bigger. So this term is bigger than 1. And so that means then that our limit, right, that the limit of a sub n, the limit of the a sub n is therefore bigger than the limit of what's left here, right? 1 times 2n over 2n minus 1. But this limit we can compute. This limit is very easy to compute. This limit right here is just equal to 1, right? It's just equal to 1. And 2n over 2n minus 1 as n goes to infinity, that's 1. And so what we have is that this limit of the sequence is bigger than 1, which is of course bigger than 0, right? And that's the key. If the terms in the sequence, if the limit of the terms in the sequence, if the limit of the terms of our series, if the limit of the terms in the sequence that make up the series, if these do not approach 0, then our series must be divergent. That's the test for divergence. So this is divergent. So divergent by our test for divergence. All right? And what that tells us then is that we cannot include 2. So we cannot include 2 as part of our interval. All right? I'm going to let you guys repeat this argument because it's basically the same. So repeat this argument here to show that -2 is also not included. The -2 is going to be alternating, but the alternating part, you'll see the rest of it is going to look just like this after you take out the alternating part. And so after all of this analysis, what we end up with is that for this series, this function, f of x, equals the sum n minus 1 to infinity, n factorial times 2 to the n, got 2's on the mind, x to the power n over 1 times 3 times 5, so the products of the first n odd numbers. This is convergent on the interval from -2 to 2. And when I say convergent, I really mean absolutely convergent on the interval from -2 to 2, but that's it. So there's our interval of convergence.